Rosen, Discrete Mathematics and its Applications, Section 12.4 on Circuit Minimization. We're studying three-variable Carnot maps here. So with a three-variable Boolean function, if we did a Boolean table, we would have 8 rows, so our K-map will have to have 8 cells. And it's a two-dimensional grid with 3 variables. One of those dimensions is going to have 2 variables. We will designate the x variable for the vertical dimension. We're going to designate y and z to be the horizontal dimension. And remember that as we go across the columns and are labeling them, we only change the complementation one variable at a time. So for the first column to the second column, we change the complementation of z. From the second column to the third column, we change the complementation of y. And then from the third column to the fourth column, we change the complementation of z again. And then if you'll note that if we go back to the first column, we've changed only the complementation of y again. So that in essence, our two-dimensional K-map is really like a cylinder that wraps around, and that's exhibited over here on the right. What that means is if we have a 1 in the upper left cell and a 1 in the upper right cell, then we can cover those with a grouping of size 2 that wraps around like that. Okay. All right, let's take a look at some example coverings. If I had a K-map that had a 1 in these two areas, my grouping would look like this. And I could reduce this two min-term expression to a single term with only two variables, x bar and y bar. In this part B, if I had a 1 in these two positions, I could wrap around like that with a grouping of 2 and change this two min-term expression into a single expression of two variables, x bar and z. For part C, if I had a 1 in these 4 cells, I could cover it with a single grouping. And in this case, the only variable that doesn't change is z bar. See, the y and the y bar are both there, so its complementation changes. X and x bar are both there, so its complementation changes. But z bar doesn't change, and so we could represent the whole grouping with z bar. And this example here, part D, if we had 1s in all these blocks, I would cover it with a grouping of size 4 in this way. And then the only thing that doesn't change in this grouping is x bar. Finally, if I have a 1s in all of the cells, I can cover it with a single map. And in that case, the whole expression always has a value of 1. So remember, the collapsible regions always have to have the size of a power of 2, and they have to be compact. They can't twist around. They've got to be squares or rectangles. All right, let's look at some examples. All right, so here we have 4 Boolean expressions in 3 variables. Number A is represented by this K-map. It's got 3 groupings to cover all the 1s, and this first grouping will have what doesn't change. X doesn't change and Z bar doesn't change. So I could write down X and Z bar. And for this other vertical grouping, Y bar and Z bar don't change. And for this third grouping of size 1, it's just going to be the min term that gives us that, X bar, Y, Z. All right, so that was number A. Let's look at number B. And that's given with this K-map. And this K-map has a grouping of 4 and a grouping of 2. Notice that we could do it with a grouping of 1, but remember we want to use the largest possible group, so we cover that 1 and we wrap it around to get a grouping of size 2. So for this grouping of size 4, what doesn't change? Well, y bar doesn't change. It's complementation. And then for this grouping of size 2, we have x bar and that would be z. So that's a nice increase in efficiency with only 2 terms. Let's look at part C. Now in this case, we've got 3 groupings of size 4. This the elongated one at the top, that is going to, the term that doesn't change there is x, so the variable that doesn't change. For this one over here on the right, this grouping of size 4, what doesn't change? Well, it's y bar. And then there's this final grouping of size 4 that's a wraparound type grouping. And what doesn't change on it? Well, it's z. Okay, finally, we'll do D. We see that it has 4 ones in it, and we have 3 groupings covering those ones. Let's take this first horizontal grouping, and that's going to be X and Z bar. Let's take this second horizontal grouping. That's going to be X bar and Y bar. And this third vertical grouping is going to be Y bar, Z bar. But notice that that third vertical grouping wasn't even needed. All the ones have been covered without it. So it was actually not essential. We could have left it off and should have left it off. All right, remember, cover the largest, identify largest regions first. Don't worry about overlap and make sure every one is covered. All right, let's get some definitions. All right, an implicant is a product of literals corresponding to a block of all ones. You could call it just a block, a grouping would be an implicant. A prime implicant is a block of ones that isn't contained in a larger block of ones. And an essential prime implicant is a prime implicant which has to be included in the final function because it's the only way to cover at least one of the ones. So let's look at that last example again. And if I had covered this one with a grouping of size 1, I would have an implicant because it's not a prime implicant because I can cover it with the larger grouping here. Now these 3 groupings of size 2 are each prime implicants because I can't put them in any of them inside a larger grouping of ones. But only the horizontally oriented of those 2 are essential prime implicants. The vertical oriented group is not an essential prime implicant. And that is our discussion of circuit minimization with 3 variables.